Good morning. This is the class for 200 DF in English of Tuesday, the 26th of May, h1h2. Okay, so I have sent you for this course a few new pages because I had to translate notes for the further chapters. One thing we will rediscuss a bit today, I already discussed it last time orally, is the heat propagation modes. Okay, we know that heat can propagate from one place to another. The question is, how does it do that? And there are three mechanisms that we know, which are conduction, which are convection, and which are radiation. So these are all very different from each other. Conduction, well, you should imagine that you take some object. Okay, let's say I will take this pair of scissors. I take that because it's metal, and metal is a good, generally a good heat conductor. Okay, so what does it mean? Conduction, it means that if I'm heating up one side of this piece of metal, the temperature is going to go up, and then the heat is going to transmit through the metal until the other side, okay? And the heat will flow at a certain rate, etc., etc. And so conduction is something we talk about only in solids, okay? There is no conduction in fluids. Fluids, we will see they work with convection. You take a solid, you heat it up. What happens? Well, let's do the experiment. Let's go. Let's be realistic. Okay? If I do this, what is happening? You see, I have my lighter and I am heating up one of the sides of the scissors. What is going on where I heat it up? Speak. Hello. Well, what is going on is that you are increasing the temperature of these scissors here, okay? So here, the thermal agitation of the atoms is increasing. These atoms who are here, who are getting hot now, hotter, let's say, they vibrate harder around their equilibrium position. They are more agitated, okay? They don't move with respect to each other, but they oscillate around a stable position. And these oscillations become bigger when I heat up the metal, okay? So here you have atoms which are more agitated, and they are in interaction with other atoms around them. So this agitation is going to propagate from one atom to the next, to the next, to the next, through the metal, okay? And that is how conduction works. And then you can take different metals and measure at which rate heat propagates. One of the best conductors for heat is copper. And of course, among the worst conductors for heat is air, for instance. Air is very bad, and all kind of heat insulators. So conduction, we will talk about that again later, is the way heat moves through a solid. Okay. Convection is something very different. Convection has to do with heating up a fluid, and when you heat up a fluid, you are always putting it in motion in some way, okay? Because let's say, let me take paper. Because let's say you have some container with, let's say it's a liquid inside. Okay, this is liquid. And now you start heating up this guy with a flame, which is here below. What is going to happen? The liquid, which is here, close to the flame, in contact with the bottom of the container, this fluid is going to heat up. So maybe I should do it in red rather than in green. Is going to heat up. If it heats up, what consequences does that have on the fluid? and if somebody wants to express itself, it will go up. But why is it going to go up? Can you tell me more precisely in physical terms? Yeah, exactly. But if you want to say it more precisely, you shouldn't say it's more heavy or it's less heavy. Because if you take a piece of metal or liquid and you heat it up, the mass will be the same. What you mean is that the specific mass is going to be decreasing. Okay? C'est la masse volumique qui diminue. Okay? So this substance here is warmer. There is more agitation between the atoms. So the atoms, they are a bit further from each other. And the fact that the atoms take more volume means that the specific mass, la masse volumique, is decreasing. Okay? And if the specific mass is decreasing, this uh, warm fluid which is here is going to go up, okay, because it's lighter than the rest of the fluid, and in a fluid atoms can move, and so it's going to go up, okay. And once it's up, what happens? Well, the fluid cannot do miracles. Once it has gone up, it must come down. Okay, so it goes up, it becomes cooler here at the other end of the tank where there is no heating. It becomes cooler, and when it is cooler, the specific mass increases again, it goes down, and so it starts turning in circles. And if you heat up water, for instance, you can do that in a pan and observe it very well. You have to put something in the water which allows you to see how it's moving. So you could imagine having tiny tea particles or whatever in the water so that you can observe the motion of the water. If you put a pan of water on the stove and you turn it on, it's going to go exactly like this. Okay, and actually inside a pan of water, you have a motion of the water all around the pan, which is leaving the center to go up and then coming back on the sides. So the water forms a kind of roll, okay? It rolls over all over the pan, and this happens in many cases, like when you have now let's consider a gas, not a solid, not a liquid. When you have a radiator in your home, okay, and let's say you have a room around this, well, what happens? You see that above the radiator, usually the walls are dirty. If you didn't repaint recently, after a few years of living in a place, it's dirty up here on the wall. Why is it dirty? Because the heater is heating up the air inside here by contact, okay? And this air which has been heated up is now going up above the radiator, okay? And when it goes up, well, it has to turn, it has to come back down, okay? But in doing so, here there is all this air which passes with dust, and the dust sticks a bit to the wall, and that's why your wall is dirty after a few years, okay? So convection is the essential mechanism for transporting heat inside glass. And the problem we have when we want to isolate a house, let's say, this is one of the big problems, because imagine you have a window. This is a window, and this window, let's say it consists of a double layer of glass with inside some gas that they put, low pressure gas, okay? Now, what happens if this gas is allowed to move, or if there is a lot of gas in there? Well, let's imagine you have on one side you have the cold, you have the outside, and on the other side you have the warm area, let's say the inside of your home. So air is a very good heat insulator. Okay, so through air, not much heat is going to pass if the heat doesn't move. But now, if the gas is allowed to move, what is going to happen? In contact with the warm glass, it's going to get warmer and go up. And when it goes up, it touches again the cold glass, becomes colder and goes down. So you have inside the window this circulation of air through convection, which allows a lot of energy to escape. So when we are doing heat insulators, we are trying to use air, but to stabilize this air, to prevent it from moving. And this is why all the materials which are like foams with small cells, okay, they are very good heat insulators because these small cells, they contain air. It's little bubbles, if you want, okay. So air is in these little bubbles, and air is an insulator. But due to the fact that there are these little bubbles, the air cannot move around, and so there is no convection, and that's why such a substance is a good insulator. Okay? Okay. Yeah. Oh, yes. Thank you. Mm-hmm. Aha. It's hard to tell whether it's the gas inside the window which is moving or if it's the gas touching the window which is moving. Because here I've done the drawing for inside the window, okay, with these two black lines representing the two layers of glass. The windows, they usually have two layers, sometimes three layers of glass, okay? So this is the motion inside the glass between the two layers. But of course, this window is colder than the inside, the window in itself, the whole thing is colder than the warm air inside. So here you will have a motion of air which is going down, okay, because it's getting cooled by the window. And outside, the window will appear warmer than the ambient temperature because it is in contact with the warm inside. Okay, so since this is warmer than this, there will be a motion of air going up. So I don't know exactly which of these motions you see. Maybe it's this one that you see. I don't know, honestly. Okay, but it's interesting what you notice that yeah, you see some motion of air um, in your window. Okay, this clearly air moves a lot more than we think. Hmm? Think about the dust which is in your house. It's not because you are dirty that there is dust. It's because human bodies they lose a certain number of dead cells and hair and pieces and things, and all this creates dust. Dust is normal, and dust also comes from the outside, okay? And you can observe very well that dust, uh, you can find it everywhere in your house, unfortunately, okay? So since dust is carried by air, this helps you understand that air is moving everywhere in a house. Indeed, air is moving everywhere constantly. Okay, and warm air is going up, cold air is going down, and all this is turning. Okay, so it's nice if you observe these motions. Did I answer your question? Yeah. Okay. Good. So we have conduction inside solids, we have convection inside liquids, and then we have another way for heat to propagate, which is radiation. So typically, radiation, I mean, our main source of radiation is the sun, okay? And radiation, we usually represent it by curly lines like this. And this radiation, which is emitted by the sun, hits Earth and, for instance, warms us up. Okay, so it is clear that there is heat which is transferred from the sun to the Earth. Now, it cannot be conduction because there is no solids between the sun and the Earth. There is vacuum. And it cannot be convection because there is no gas in space. Okay, there is no gas to have convection. So what is left? Well, it's a mechanism which we call radiation, rayonnement ou radiation en français, radiation through which the sun sends us heat. And what is this radiation? Usually it's photons. These are very tiny particles. These are the particles which form light, but they can also form other types of radiation, electromagnetic radiation. And this electromagnetic radiation is able to propagate in space. Okay, it's able to propagate in a vacuum. And this is the only mechanism of heat conduction that can propagate in the vacuum. Okay, so now to give you an example, again, with my radiators, because when I talk about that, I always talk about radiators. Let's assume we have a wall, we have a radiator here, okay, and you are standing here, okay. How do you get the heat from this radiator? Of course, you get the heat because there is a circulation of warm air due to convection, of course. But there is another way in which you are now going to receive radiation from this radiator. This radiator is going to send in all directions, and so in particular in your direction, this radiation is going to send out electromagnetic waves which carry heat. So maybe usually it's infrared radiation which carries heat. Okay, infrared allows to heat up at a distance something. So if you have a radiator in your place, choose a day where it's nicely warm, pass in front of it, and you will see that when you pass in front of it, you feel it. You feel that it's warm. It's because this heat, which radiates, directly hits your skin. Okay, well, listen, I've discussed that last time already. Maybe I should not be spending all this time on that. Let me just find my course here. Okay, let us illustrate that. Okay, we have here the three mechanisms which are illustrated in these two pictures. Here we have a fire. Okay, this fire is heating up the air around it. So above the fire, the air is going up, and in this warm air, you can warm your hands. This is clearly convection because it involves a motion of the gas from the heat source to where this heat is used. Okay. Now, if you put a bar of metal inside this warm air above the fire, of course, this bar of metal is going to warm up here, and this heat is going to transmit through the bar, and finally, it's going to hit your hand. But it's going to hit your hand by traveling through the metal. Okay, so this is conduction. And of course, if you hold your hands near the fire, not on top of the fire, but next to it, what you feel on your hands, what is warming up the palms of your hands, is radiation. Okay? Another example down here with a pan. You see in the pan they have illustrated this motion of the water. So this motion represents convection. You can burn yourself if the handle of the pan is conducting heat. Okay, so here there is conduction through metal. And of course the fire doesn't only warm up the water, but it also produces radiation, which is going to warm up any object which is close to it. Okay, so I talked about this last time. There is not much more to say. Let's say if we want to go at the level of equations, etc., it will take us way out of the program of the college. So we just mention these things, but already the fact of knowing them is kind of interesting, in particular when you need to discuss the isolation of your home and stuff like that. Okay, you have more questions about that? Oh, yes, yes, I will tell you. They work with magnetic fields. Okay, when you have a plaque à induction, what you have under your pan is an induction coil. You know, the symbol for induction resembles that. When you want to buy a pan which is certified for induction, it should have a symbol like that. You've seen that? Okay, and what does it mean? Actually, this means that there is an electrical wire under the pan, which produces a magnetic field. Okay, so this is a self, une bobine en français. It's a wire which is going around many times. Okay, and through this wire you have a current which is passing. Okay, and this current is going to create a magnetic field inside the coil like that. You will see that in the third year. Okay, if you take a current through a coil, it's going to generate inside the coil a magnetic field, and this magnetic field is going to look something like that. Now, I'm just showing the principle. I don't know much about the real technology of induction. Okay, what I know is that you have these coils, bobine, which produce a magnetic field. The current here is an alternative current, so the magnetic field is alternative. And now on top of that, you are putting a pan made out of metal which contains something and you want to warm it up. Well, what happens? This oscillating magnetic field that you have produced here obliges electric charges to oscillate inside your metal. Okay, these magnetic fields, they put in motion the electrons which are in the metal of the pan. And so that's why you need specific types of metal, because in some types of metal there is a motion of electrons inside when you have a magnetic fields, and this is fine. And in other types of metal this doesn't exist. So if you want to heat up aluminium with that, you cannot. Okay, it has to be a certain type of iron composite. And so these charges here, they move across the bottom of the pan, but the currents which I'm talking about are quite big. Okay, there's a lot of motion of charges, and if you have charges moving in a metal, this causes the metal to heat up because there will be shocks between the electrons which are moving around and the atoms of the pan. So this motion of the electrons is going to heat up the bottom of the pan, and the bottom of the pan in turn is going to heat up whatever is inside. Okay, this is why induction stoves, they don't get warm, because this guy here, the generator here, does not produce heat. It produces a magnetic field, and then the effect of this magnetic field is to warm up the bottom of the pan. So it's the pan which is warming up, and by contact with the stove, the pan is warming up the stove a bit, but it's never burning. And that's the good thing about induction. And the other good thing is that it's very fast and very reactive. Okay, so it has the advantages of gas and the advantages of electric heating. Did I answer your question? Okay, so it's an electromagnetic system. Okay. Good. Okay, so now let's continue. This was just a small revision. There's another subject I want to talk to you about. From the theoretical point of view, it's not something very interesting because the laws we are discussing, they are very simple. But it's something relevant for everyday life. It's dilations. Dilatation en français. Okay. What is a dilation? Well, if you take an object at a certain temperature and you heat it up, this object is going to expand a bit. Okay. If you take a wire and you heat it up, this wire is going to become a bit longer. Why is that? Because you increase the thermal agitation of the atoms, and so these atoms, they tend to sit a bit further from each other. Okay, not much, but since we have so many atoms in substances, this very tiny separation of the atoms results in a dilation of the whole object. Okay, so objects tend to dilate when they get warm, and they tend to shrink when they get cold. Okay, and that's the reason, for instance, why you have this kind of things. I don't know if it printed out well on your course. This is what you can see at the beginning of almost any bridge in the world, and this, you have it on the Pont du Mont Blanc. Clearly, you can see it very clearly at the two ends of the bridge. It's a system like that, like a cam, where the bridge, this is the end of the bridge, this is the beginning of the road on the other side. The bridge and the road, they have a system which allows the bridge to dilate. Okay, this here, this space which is left here, of about, how much is it, 15 centimeters maybe, if I look at the image, this space is space which is allowed for the bridge to expand a bit. Okay, let's assume maybe the temperature here is 20 degrees. When the temperature will be 40, the bridge will be longer because it dilates, and so we need to have some place where we can absorb this increase in length, and so that's why at the end of bridges you always have systems like that. Okay, it's to allow for dilation. This is also why, if you look at railways, if you look at the way the rails are built, okay, how is it? You have one rail which arrives here. Let me try to draw a rail properly. Okay, yeah, it's something like that. Okay, let's say this is one rail. Okay, well, the next rail is not right next to it. There is a little space. Okay, and why is there a little space here? Because this is to allow the rails to dilate. Okay, so these holes between the rails, they are bigger in the winter than in the summer, because in the winter it's cold, the rails are shorter, and so these spaces between the rails, they are increasing. Okay, and they can reach 2 centimeters, 3 centimeters maybe. Whereas in the summer, let's say the temperature is 40, the rails are very warm, they have dilated, and so this hole here closes. Okay, and these holes, they are the reason why when you ride a train, you hear this tack 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 tack. You know, the typical noise of trains. Why is it tack tack? Because you have, on the bogies, you have two series of wheels. Okay, so first series and then second series. A train bogie is done like that. Okay, and so when it passes over a separation between two rails, you hear it first here, then here. So it's done the tack tack, and the tack 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 comes from the next separation. Okay, tack 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 tack, etc. Okay, what I want to say with this is that you can do one observation regarding that. You can observe that in the winter, this tack 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 noise of trains is much stronger than in the summer, because in the winter the holes are bigger. Okay, so the wheel of the train falls into it a bit more, if you wish. It doesn't fall into it, but it produces noise a bit more in the winter than in the summer. And you have all kinds of problems. Railways are great to study dilations. Okay, when you have, let's say, you have a railway, and here you have your all your systems supporting the electric cables. Okay, when the weather is cold, okay, the wires which give electricity to the train, let's say the trains are here, and there is this thing here on top of the train which allows the train to obtain electricity. Okay, well, when the weather is cold, this is fine, the position of the cable is nice. But when the weather is very warm, what happens to these cables? These cables, they dilate. Since they dilate, they become longer. So your cables in the summer tend to do this. Okay, they tend to miserably go down to the, not to the floor, but I mean they are lower, and they are not tense enough, and so the trains, they can no longer ride. Okay, it doesn't happen in Switzerland so much, at least I don't remember having heard of it, but in France, very often, when the weather is very warm in the summer, they cannot have the TGV running. Or if they run, they will run at a lower speed, because there is a danger that then that with these cables which are dilated, there is some kind of accident, and maybe the train is going to break the cable, and it's going to be a mess. Okay, so yes, we have to be careful about dilations. Okay, in many areas. Okay, it was a long discussion. Are you still with me? Okay. So let me now look at the laws for dilation. I don't know why there is a cross which appears here. There was no cross last night. I don't know where these crosses are coming from. Whatever. Okay. It's not my habit to mark the products with a cross. This is kid stuff. But in here it's done, and it's too late for me to correct it. Okay, so we will consider dilation of solids, dilation of liquids. Okay, if we and then dilation of gases. If we consider dilation of solids, then as you can imagine, the length difference, so the delta L, is just the final length minus the initial length. Okay, the delta L is proportional to the initial length. Of course, the more the initial length, the more the dilation. Okay, if you take the dilation of a 10 centimeter piece of iron and the dilation of a 10 meters piece of iron, there's going to be a factor between them. Okay, so the increase or decrease in length is given by the initial length times the temperature difference, okay, times some coefficient which has a value, and these values you can find in the table. So these rules are not really physical rules. They are not very deep physical rules. They are phenomenological rules which just try to mimic what is going on. Okay, try to explain what is going on in a macroscopic way while the phenomenon is microscopic. Okay, so for linear dilation, the increase in length is some coefficients times the length times the temperature difference. Now we can, this is for the dilation of a thin piece of metal, typically a wire. Okay, but now if you're interested in the volume dilation, then you have another formula which looks very much like this. The volume increase or decrease is proportional to the initial volume, to some coefficient which we call gamma, and to the temperature difference. Okay, and this gamma, it turns out, is just equal to 3 times this alpha. Okay, so when you have to study the volume dilation of some material, well, you look for the coefficient of the linear dilation, you multiply it by 3, and you get your coefficient here, and this allows you to compute your delta V. Okay? And all these laws, they're basically all the same. Now, if you look at the dilation of liquids, well, the dilation of liquids, you cannot put a liquid in a string. Yeah, you can put it in a container which has the shape of a string, but it's cheating. Okay, for liquids, the only thing we are going to be interested about is in the variation in volume. We don't talk about linear dilation for a liquid. And for a liquid, we have again the same formula. Okay, it's the same phenomenological type. For the increase or decrease of volume, it's a coefficient times the initial volumes times the temperature difference. As is said here, this coefficient, which we also denote gamma, now has a value. You have to look for the values in the tables. And for liquids, this coefficient is generally 10 to 100 times larger than for solids. So liquids, they dilate and contract more than solids with temperature. Okay. For instance, do you know one system which uses liquid dilation to measure temperature? Hello? Wake up. The thermometer. Okay, the thermometer is a container in which there is a liquid, and this liquid has a certain volume at a certain temperature. If you increase the temperature, the volume of the liquid increases, and so since the volume increases, it needs more space, it goes up. And when the temperature decreases, the volume of this whole thing decreases, and so the top of the liquid goes down, and so you can read your temperature. Okay, so a thermometer, this type of thermometer is essentially based on the dilation of a liquid which is inside, which is usually water with something. Anciently we had mercury, but mercury is dangerous. Now we don't all have mercury. Okay. Here just a small comment about water. Water has an anomalous behavior. And so if you see, this is a table of the density of water as a function of temperature. Okay. And look at the numbers. This is the temperature 0.1 centigrade, 1 centigrade, 4 centigrade, 10, 15, 20. And this is the density of the water. Okay. What do you observe? You observe that at 4 degrees Celsius, you have a maximum. Well, it's not so easy to see, but if you compare to the other numbers, okay, really the water has a maximum density at 4 degrees. And so that's why the water likes to be at 4 degrees. This is because at 4 degrees, it can maximize its density. And so this is the reason why the oceans, they have a temperature of 4 degrees, okay, except the surface layer, which is warmer. But then as you go deep into the oceans, the temperature is uniformly 4 degrees. Okay, and now what about the dilation of gases? Well, the dilation of gases is again given by the same formula, some coefficients times the volume times delta T. But now for gases, we have the fact that gases behave in mostly the same way. Yeah? Because a gas, you can see it as a collection of point-like particles, the atoms, which collide between each other. And whether these atoms are big or small doesn't matter much with respect to their separation. And so when you have a gas, under certain conditions of pressure and temperature, so if the pressure is not too crazy, if the temperature is not too crazy, all gases behave kind of the same. And they are called, this is a model called the ideal gas model, which we will see in a moment, And so all these gases, they respect this law with a gamma, which is given here, which is the same for all gases, is 0.0037 1 over Kelvin. Okay? Good. So let's try to work a bit on that. You want to try to do the first one? Okay, a rail made of iron is exactly 100 meters long at 10 degrees. How long is it at 35 degrees? Well, you want us to do it together? You want to try to do it? Which is the law you need to use? Okay, it's a rail. So what we are interested is the elongation of the rail. It's the delta L, okay? And we saw that the delta L is given by some coefficient alpha times the length of the rail times the temperature difference. Good. Now we need the coefficient alpha, okay? So where are we going to find that, you think? Hello, hello. Are you still there? You don't know. In the CRM table. So let me see if no, I don't have it here. Mass volumic. Okay, it's still in the same tables in the CRM. You know these tables, we don't have them at the same page, but you know them very well. They're about in the middle with all the substances and the various characteristics on 2 pages, okay? So let's go to iron, fer, and actually it's the first of the 2 pages, okay? So I have iron here, okay? And then here I have a line, you see, coefficient de dilatation. You see that? Okay? And this is what we need. It's indeed what I told you. It's in 1 over kelvins as the unit. It's called alpha. And sometimes they also have the gamma for substances. For instance, for liquids, you don't have the alpha because there's no linear dilation, but you have only the gamma. Okay, if you look at the 4th line, this is alcohol, so you don't have the value for linear dilation, you have a value for volume dilation. And the next line, it's aluminium, so you have the coefficient for linear dilation, and this coefficient, you should know that it's just 3 times this one, okay? So now let's look at the iron. Iron is this line here, okay? And so we have the dilation. Oh, sorry, you don't see. Okay, iron is here, fer, and so we have the dilation coefficient of the iron, the alpha, the linear dilation coefficient, which is 12 times 10 to the minus 6 Kelvin minus 1. Kelvin minus 1. Okay, so alpha is 12 times 10 to the minus 6, 1 over Kelvin. Okay, and now with this, try to answer the question. Okay, what is your unknown? Well, once you compute delta L, you should find delta L, and then the final length is going to be L plus delta L. You want 5 minutes to do it, or you want me to do it? Huh? Answer. Sorry? First I do it. Okay. So we have this delta L which we need to compute. Okay. The value for alpha, we know it. It's 12 times 10 to the minus 6. We know it because it has been measured. Okay. As I told you, it's not a very deep physical law based on microscopic phenomena or whatever. It's a law which describes by how much a rail of metal is going to dilate when you warm it up. So L is the initial length. The initial length is 100 meters. And the temperature difference, delta T, this is the final temperature minus the initial temperature. Okay, we want this delta T to be positive in case the final temperature is higher than the initial temperature. So this is fine the way it's defined. because if the delta T, if the temperature increases, we want the length to increase. So if the temperature increases, this difference has to be positive. It's normal, okay? And when the delta T is going to be negative, it means the delta L is negative, so you're going to lose length. Okay, so now 1.2 times 10 to the minus 6 is the constant, 100 is the length, and delta T is the final temperature, 35 degrees, minus the initial temperature, 10 degrees, 10. Okay, voila. And so now we compute that. It's 12 times 10 to the minus 6 times 100 times 25. And how much is that giving us? 12 times 100 times 25 divided by 1 million. This is equal to 0.03. 0.03 what? What's the unit here? You again closed all your microphones, huh? Meters, yes, it's length, We used all the right units. By the way, let's check the units. These are 35 minus 10 is degrees, okay? The 100 is what? The 100 is meters, and this coefficient, we said it's Kelvin minus 1. Okay, so let's say here we take the temperatures in Kelvin, it compensates this 1 over Kelvin, and we are left with meters. Why Kelvins and Celsius? Why do I change so easily? Because here it's a difference. So the difference between 35 minus 10 in Celsius is exactly the same as the difference between 305 and 280. Yeah, whatever. It's the difference here in Celsius is equal to the difference in Kelvin. So I can say Kelvins or Celsius here. Okay, it's 0.03 meters. So it's 3 centimeters. Okay, so you see a rail which has a length of 100 meters. Honestly, I don't think rails are that long. I think they are less long. But last night I edited this problem and the initial length was 1 kilometer. I thought, no, that's not possible. A rail of 1 kilometer, you cannot lay it down. Okay, so let's say 100 meters at 10 degrees. Well, if you increase the temperature by 25 degrees, your rail is going to be 3 centimeters longer. Okay, so on each side it's going to pick up 1.5 centimeters. And so you need a space of at least 3 centimeters, 2 times 1.5 every 100 meters, if you want to be able to accommodate a change in temperature from 10 to 35. If you want to be able to accommodate a change in temperature which is larger, like minus 20 to plus 40, which would be more suited to our areas, then you need a bigger separation between the rails. Okay, or then maybe you need to use shorter rails so that you can have more of these expansion areas. If you have more, you can make them shorter. Okay, ça va? You got it? Do you want to do the next one? Do you want to try it? Shall we do it together? As you like. I don't know. Let me just remove my sweater because it's starting to feel warm. You want to try to do it? Shall we do it? Let's do it. Okay, we measure the length of an object made of an unknown metal. At 20 degrees, the length is 1 meter. Okay, so at 20 degrees, the length is 1.000 meters. I recall you, in case you have forgotten from the IDS class, I recall you that this means that this gives us an information about the precision of the measurement. It means that if we give these zeros, it means that we have measured them. So we know it's exactly 1 meter, 0 decimeters, 0 centimeters, 0 millimeters. Okay, so this is 1 meter plus or minus half a millimeter. And we heat it up, and at 60 degrees, this guy has a length L prime, which is 1.001 meter. So it has increased by 1,000. Okay. And now the question is, what is the coefficient of linear dilation? The coefficient alpha. We should now compute this coefficient. Okay. So, well, let's write the equation first of all. What is the equation we need to use for that? We need to use the equation which gives us dilation, which is this. Okay? It's the equation, it's this one for the linear dilation of solids, right? And what do we know inside this formula? We know delta L. What is delta L? Delta L is L prime minus L. Okay, L prime minus L is 1 millimeter. So delta L is 0.001. Right? Now we know L, the initial length. The initial length is 1.000 meters. And we know delta T. Delta T is the final temperature, 60, minus the initial temperature, 20. Okay, so delta L is 40. And the alpha we need to determine. So this gives us a very nice formula for alpha, because alpha now we can isolate it from this equation. And so we can write it as delta L divided by L delta T. Okay? Does that make sense? So now the delta L is what? Is 0.001 divided by the initial length, which is 1, times the delta T, which is 40. Okay? So it's 0.001 divided by 40, and this gives me 0. So it's 2.5, 1, 2, 3, 4. Okay, it's 2.5 times 10 to the minus 5, 1 over Kelvin. Okay. That was question A. Now question B, let me do it here in this small hole. Question B, what is the coefficient of volume dilation? What would you answer to that? What did we say? I don't know if you remember. Okay, we said that the coefficient for volume dilation is just given by 3 times the coefficient of linear dilation. If you want to remember it, you can think that, well, when going from 1 dimension to 3 dimension, you have to multiply by 3. Okay, and so your gamma is not going to be 2.5 times 10 to the minus 7, but it's minus 5. It's going to be 7.5 times 10 to the minus 5, 1 over Kelvin. Okay, this is going to be the coefficient of volume dilation. And now, what can you spot a possible material with these properties? So I have no idea what substances I had in mind when I was writing that, but let's take the table, okay? Let's take the dilation coefficient and look for one which is 2.5 times 10 to the 5. 2.5 times 10 to the minus 5. Here you have aluminium. It's 23 times 10 to the minus 6. So this is 2.31 times 10 to the minus 5. It could be aluminium, okay? It's not going to be iron because iron is 12 times 10 to the minus 6. And let me see in the rest of the table. I'm sorry, I'm without my glasses. Aha. What is that? Magnesium. Okay. We have here a value which is very nice. 25 times 10 to the minus 6, which is equal to 2.5 times 10 to the minus 5. So this is our guy, okay? We found in the table a substance, a solid, with a linear dilation coefficient of 2.5 times 10 to the 5. So this is magnesium. Do you know what magnesium is, ladies and gentlemen? Do you know? It's a metal. Yeah, magnesium is a metal. My former laptop was made out of magnesium, which is very nice. Okay, this is my old laptop. This is my old laptop here, and it's an HP, and the whole body of this laptop is made of magnesium, not aluminium. So it's stronger than aluminium, and it's also lightweight, so it's very convenient to do this kind of things. But then magnesium, it's also a chemical that is quite important for your health, because if you have too little magnesium in your body, you are starting to have cramps, and you are starting to have something which many people have, which is not nice to have, is when you go to bed in the evening, you lie in your bed, you try to sleep, but your legs don't let you sleep because they are kind of shaking. They are kind of tickling inside, okay? This is called restless legs syndrome. And restless legs syndrome comes from the lack of magnesium in most cases. So if you feel this kind of things, if you feel nervous in a period of exams, etc., think that you may need additional magnesium, because modern food, processed food, is removing magnesium from the food, and so we usually don't get enough magnesium. It's very easy. You buy magnesium pills at the pharmacy or even at Migros. You put them in a glass of water. It gives you a nice drink. I like these drinks. You drink that and you feel better immediately. So think about your magnesium. And if you don't want to run out of magnesium, eat raw products. Don't eat white bread, eat dark bread, etc., etc. Okay? And of course, you should eat lots of dark chocolate and what else? Apples, apple juice. It's very good for magnesium. But be careful not to take too much magnesium, because you know what it does if you take too much. Huh? You have an idea? No. No, it gives you a lot of diarrhea, so don't exaggerate on magnesium. This is why when you drink lots of apple juice, you have diarrhea, because of the magnesium. Whatever, this is a course of physics. What is the volume of oil which, when getting heated from 20 to 100 degrees, sees its volume decrease by 1 cubic centimeter? Aha. So you see, this sentence sounds complicated. So what do you do in these cases? You write the formula, and then you try to interpret these sentences in terms of what they mean for the formula, okay? So we are talking about volume dilation, okay? It's volume, so volume dilation, delta V, is given. This is a liquid. It's gamma V delta T. And what did we say about the liquids? We said that, yeah, it's gamma V delta T is here. And we said that these parameters, gamma, they are generally higher, but we still have to look in the table, okay? Good. So this is oil. Aha, oil. So we need the gamma for the oil. Okay? But let's see first of all what the sentence says. Which is the volume of oil? So we need to compute the volume, V. Okay? So we are going to need to invert this formula to compute the volume, and the volume will be delta V over gamma delta T, very simply. Then the delta T, we heat it up from 20 to 100, so the delta T is the final temperature minus the initial temperature. Okay? And the gamma, we should look for it in the table, gamma of oil. Okay, let's hope there's not 5 types of oil in the table. Oil, huile, hydrogène, huile. Okay, we have 4, not 5. Huile d'arachide, huile de chauffage, huile d'olive, huile de transport de chaleur. I will take olive oil. I will take olive oil, but I'm not at the right page. So let me go to the next page. I will take olive oil because I like olive oil. Okay, I cook everything with olive oil. Olive oil, aha, we don't have the coefficient. Why we don't have the coefficient? Oh yeah, no, we have helium. Okay, we have only one coefficient. We have one for heat transmitting oil. Okay, so I don't have a choice. I'm going to take this one. 7 times 10 to the minus 4. You see that indeed these coefficients, they are bigger than the ones we saw before for solids. Okay, 7 times 10 to the minus 4, 1 over Kelvin. 7 times 10 to the minus 4, 1 over Kelvin. Okay, and in the problem, they tell you that when submitted to that, sees a volume increase by 1 cubic centimeter. Okay, so the delta V here is 1 cubic centimeter. But of course, we cannot compute with that because we need to be in cubic meters. Okay, so 1 cubic centimeters is how much? It's 10 to the minus 3. It's 10 to the minus 3 cubic decimeters, and so it's 10 to the minus 6 cubic meters. Okay? You always need to do the computations in the basic units. Good. So now we have all the values in the right units. Okay? So I will now compute that. The delta V, we said, is 10 to the minus 6 cubic meters. The V, the initial V, the initial V is our variable. It's here. We don't need it. The gamma is 7 times 10 to the minus 4, and the delta T is 80. Okay? 10 to the minus 6, 10 to the minus 4. There's a 10 to the minus 2 remaining. So it's 10 to the minus 2 is 1 over 1. It's 0.01. Now divided by 7, divided by 80. And what I find is 1.79 times 10 to the minus 5. What unit? Are you still there? Or you're just having coffee and... Sorry? Here is cubic meters. Okay? So 179 times 10 to the minus 5 cubic meters. How much is that? This is 1.79 times 10 to the minus 2 cubic decimeters. This is 17.9 cubic centimeters. Is that possible? That sounds like a lot. that 17.9 cubic centimeters can increase by 1 cubic centimeter, but apparently it's the result of the calculation. It sounds like a lot. No, it's okay. Looks okay. Okay? So all these exercises, they use the same formula and they make you dig out one of the parameters. Okay. We are going to slightly change chapter. It's not going to be very long. I'm going to do it fast. It's now the concept of ideal fluids. Okay, as I told you before, most fluids, you can treat them, and especially gases, you can treat them as if they were composed of an assembly of particles, which are all basically moving, which are all basically behaving in the same way. And so you can derive global properties with phenomenological laws like this one. So historically, there have been three laws which have been derived, one by Charles, one by Gay-Lussac, and one by Boyle-Mariotte, but all these laws are contained within one law, which I will explain you in a moment. So basically here, what we are looking at is the interdependencies between pressure, volume, and temperature. These are very basic parameters for gases and liquids, okay? Pressure, volume, temperature. And how are they related to each other? So each of these guys, Charles, Gay-Lussac, and Boyle-Mariotte, well, these are two guys, they fixed one of these parameters and they saw how the others were behaving. So Charles decided to work at constant pressure. So he has an enclosure of gas at constant pressure, and he's trying to see the relationship between the volume and the temperature. You want an image of that? You take a bag, you fill this bag with air, you don't make it tight, so the pressure inside the bag is always atmospheric pressure, and you heat it up. What is going on if you heat up the bag? It's going to expand. The volume is going to increase. So this means that the volume is proportional to the temperature, or volume divided by temperature gives a constant. This is the first law, okay? It means that the volume is proportional to the temperature. Maybe I can use this symbol. Volume is proportional to the temperature at fixed pressure. Okay. Second law, it's a Gay-Lussac law. Gay-Lussac decided to fix the volume. So he was having a definite volume of gas, and in this gas, he was changing the pressure and the temperature. Well, what did he see? He saw that if you increase the pressure, you also increase the temperature. So the pressure is proportional to the temperature, but this is at fixed V. Okay? Yeah. Yes, the loi des gaz parfaits is this one. It's coming in a minute. Okay? These are historical preparations to the law of ideal gases. Okay, so Gay-Lussac noticed that at fixed volume, P and T are proportional. So if you put more if you pressure, if you oh God, I'm sorry, I'm tired this morning. If you compress, yes, if you compress a gas, its temperature is going to increase. You know that very well if you ever pumped the tires of your bicycle. The pump becomes warm when you pump. It's because the air, which is now under increased pressure, has increased its temperature. Okay, and then there's the law of Boyle and Mariotte, in which they work at constant temperature, and at constant temperature, you know that if the pressure increases, the volume will decrease. If you increase the pressure, okay, the volume of your thing is going to decrease. So these are inversely proportional. The pressure is proportional to the inverse volume, and so P times volume is equal to a constant, and this is at fixed temperature. Now there is a way to state these three laws together. You see V over T, P over T, P times V. You can combine them all into one law, which is called the ideal gas law. And most gases, if the conditions are not extreme, most gases will follow this law. Okay, so this is in French, la loi des gaz parfaits. The gas parfait, the ideal gas, is a model. It's a model of a gas with point-like particles interacting each other only by shocks. But most gases under decent conditions follow this law. So we can do a lot of things with this law. Okay? This law, we write it like this for kids. Then when people grow up, we write it a bit more precisely, like this. And then you have various formulations of this law, which is a very important one. You have a formulation for chemists, you have formulations for biologists, it can become a mess, okay? Let's stay at this level. What are these guys? P is the pressure, V is the volume, T is the temperature, and N and R are constant. R is the ideal gas constant, it has this value, and N is the number of moles. Okay, so I'm not going to go into these details, it's just to tell you that there is more to the law of ideal gases than this very basic formulation. Okay, you can do it more precise. And now I have three problems for you, and then I will be done. Okay. Problems are, the first one, a gas occupies a volume of 1 cubic meter at 10 degrees, at 15 degrees. This same gas occupies a volume of 1.1 cubic meters at an unknown temperature T. What is this temperature? Okay. You have a bag of gas in your house, which is 1 cubic meter when the house is cold. And for some reason, you want to know how big this bag is, at what temperature this bag is going to increase in size by 10%. Okay, so how do you do that? Well, you don't necessarily know how to do that, so I will tell you. Okay, we are going to work with the easy form of the equation, because if we start with moles, etc., it's a mess. We will use this form. Okay, we know that P times V over T is a constant. Okay, if it's a constant, it means it will have the same value in the first situation when the temperature is cold, and in the second situation when the temperature is higher. Okay, so we are going to write that P1 V1 over T1 is the same as P2 V2 over T2. Sorry, I wrote in the bad. Sorry. P1 V1 over T1 is equal to P2 V2 over T2. Okay, where P1 is the initial state of the gas. Okay, does this exercise mention a change in pressure? Okay, because I'm trying to find the values for the pressure. Here, apparently the pressure has not changed. Okay, so we can say that P1 is equal to P2, and actually, if I don't take care of the pressure, this is equivalent to using one of the laws I showed you before, the one at constant P. And the law at constant P is Charles' law. V over T is equal to constant. So this is all consistent, okay? If you fix the pressure in this law, you get this law. If you fix the volume in this law, you will get this law. And if you fix the temperature in this law, you will get this law, right? So that's why, I do it because it's nice historically to see that. But these equations, they are all contained in the equation of ideal gases. Okay, so we said P1 is equal to P2. This is a constant pressure. Now, what do we want to know? We want to know T2, right? So V1 over T1 is equal to V2 over T2, means V1 T2 is equal to V2 T1. I just did the cross product, okay? And now we need T2. So T2 is going to be V2 over V1 times T1. And that's it. We're done. We have it. Okay? Because we know V2, we know V1, we know the initial temperature. So V2 is 1.1 cubic meters, the final volume. The initial volume is 1 cubic meter, and the temperature T1 is 15 degrees. Okay? I am wondering now if I should use Kelvins. Let's see what it gives us. No, it's correct. 1.1 times 15 is just 16.5 degrees. Is that correct? 1.1 times 15, yeah, 16.5. Okay. It sounds a bit strange, but listen, what I did is wrong. What was wrong? What would you say was wrong? Because I don't believe in this result, okay? It's not by heating up the gas by 1.5 degrees that you are going to increase its volume by 10%. I don't believe it, okay? Always, when you compute something, try to see if you can believe it. What is the big mistake I did in that problem? I think it's a big mistake. Yeah, we need to use Kelvins because here we are not dealing with temperature differences. We are dealing with absolute temperatures, okay? And this law starts at the absolute zero. I mean, there is no reason for this temperature to be zero at the phase transition of the water, okay? So let's now use temperatures in kelvins. I told you weeks before in the course that at some point we would need to use kelvins, and let's see what difference it makes. You see, I've done a mistake and now I'm reusing it as a pedagogical argument. It's so smart and I look so much less stupid. So T1 is 15 degrees, but how much is 15 degrees in kelvins? 15 Celsius. It's 273 plus 15 Kelvin, okay? And so it's 283, it's 288 kelvins. Don't say degrees, say kelvins. Okay, so here I should use 278, and T2 is going to be in kelvins. And let's see now what it gives us. 278 times 1.1, 278 times 1.1, and this gives us 305.8 Kelvin. Okay, and 305.8 Kelvin is 32.8 degrees Celsius. So this I'm more ready to believe. If you pass from 15 degrees Celsius to 32.8 degrees Celsius, yes, the volume may increase by 10%. But what I computed before, this seemed completely crazy. That when you increase the temperature by 1.5 degrees, you could have a 10% increase in the volume. I don't believe it. So this is why when you compute something and when you see a result, please take that as a habit in your life. When you see a result of a calculation, don't just write it down stupidly. Ask yourself whether this is possible, this is feasible, this is acceptable or not. Okay? Good. So for this kind of problems, we really need to use the Kelvin scale. Okay? You want to do the next two? Well, it's time now. Listen, what do we do next week? Because next week, normally, we still have courses. We meet, we finish the exercises. Is that okay for you? Okay? So let's do it like this. I give you these two exercises for next week. I will not have, I'm not going to artificially write a new course, okay? But maybe we can have a discussion. It would be nice if for the next lesson you can prepare some questions maybe that we can discuss together. So this would be for June. What is it going to be next week? It's going to be June 2nd, okay? June 2nd, and you can try to do these exercises for next week, okay? Ça marche? Allô, allô? Let me just see with online whether I forgot. Oh, everybody's here. My God, what a class you are. My God, if I compare you guys to my first year students of Tuesday afternoon, my God. So now there is everybody. Alexandre, yeah, you are 14. So who is missing actually? Frida, is she here? Frida, yes, she's here. Santiago, is he here? Yes, Santiago is here. Isalis, is she here? Would be nice if you could speak. No, I don't see Isalis. Naima, is she here? I don't see her. And Emma, I guess she's here. Emma, yes, she's here. Okay, well, it's impressive. All these students, so serious. Okay, I hope you liked it this morning, and let's meet next week, and we can discuss about thermal stuff, isolation, whatever. There are lots of things that we can discuss. Okay, have a good day. Bye bye. See you next week. Bye bye. Bye bye.